Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to wrap up our examination of free energy by looking at kind of a nuanced topic known as fugacity. So fugacity is kind of an infamous topic because it really deals with how we deal with a non-ideal gas through a couple of hand-wavy shenanigans. And if you're interested, here is a link for an actual rather funny comic series written by a chemical engineer known as Dante Shepherd, talking about fugacity, really oriented towards chemical engineers. So I'd highly encourage that if you feel a little confused after this first pass through. So one of the most important things to remember is when we're looking at the free energy of a gas is really what we'd like to do is describe the free energy of any gas based on its reference standard state and essentially a nice simple pressure correction. However, remember when we derived this pressure correction, we assumed an ideal gas. And that means that if we have a non-ideal gas, this equation doesn't work. So one of the classic tricks that you can go ahead and use, and this is very common as you've seen in any number of things, is we'll keep using the same equation, but we replace the pressure with more or less a fudge factor known as fugacity. So fugacity is the effective pressure if the gas was ideal. So what we've done is we've said, okay, this gas isn't ideal, but if it was ideal, this would be how it would act. This gas would act like a ideal gas with a pressure of 2 bar, 3 bar. And that's what the fugacity is it's a way of saying how does the gas act, not what is its actual pressure. And note the fugacity will only ever really be used in equations that depend on free energy. So it's mostly going to be used in this expression or other ones that are derived from this. Now, what we can do is we can relate the fugacity to the actual pressure through this nice simple equation where this phi is known as the fugacity coefficient. And the fugacity coefficient really is our true fudge factor. So if the fugacity coefficient is 0.7, it means that the gas acts like it has only 70% of its pressure. If it's 1.3, it acts like it has 30% more pressure than it actually does. And so that's really what that coefficient can be thought of is the ratio of the effective pressure to the actual or ideal pressure. Now, trying to actually determine this is a little difficult as you have to do it by using the differences in free energy properties in between the real system and what this ideal system would act like. Because remember, this fugacity is only acting through these sort of free energy interactions. So we can do this. So the best way to get this is comparing the free energy for a system uh, with an actual pressure of P to whatever its fugacity would be. Now we can go ahead and insert in the expression, again, knowing that it's going to follow this same general relationship, as the free energy of a system with a fugacity F can be obtained by comparing that standard state free energy, because that won't change. And then again, this same pressure correction where we're going to integrate from 0 to whatever the fugacity is, because the fugacity is going to act like it's ideal just with a higher pressure, but it will still use the same equation. Now, we can do this compared to the actual pressure of the gas. Now, when we do this, you can go ahead and note when we distribute this out, the reference pressure will disappear in both cases. So what we're really going to be comparing is these two integrals. Now, when we do this, because again, we're assuming the system behaves ideally, even if it doesn't actually, that's part of the reason we can use the fugacities. We're assuming ideal behavior, we're just changing the ending value. We can then insert the ideal gas expression for both of these molar volumes. That way, it should be relatively simple to integrate because note, these RT terms should come out in front of the integral. And what we're going to be left with is, again, this dp over p from 0 to f and dp over p from 0 to p. Now, If it's dp over p, that means we just get integrals of natural log. And the natural log of 0 is just going to be 1. So we can directly compare RT natural log of the fugacity to RT natural log of the pressure. Now, using log laws, I can go ahead and combine these by using a ratio of the fugacity to the pressure. Well, as we see up here, the fugacity over the pressure is just the fugacity coefficient. That means the difference in between the real and the ideal behavior, or the real and ideal free energy, is just going to be based as RT times the natural log of the fugacity coefficient. Now, what this means is we need a good way to determine the fugacity coefficient for this system. Well, to do so, what we can go ahead is start again with our expression. So we've got the natural log of the pressure over the fugacity coefficient. Well, this lets us go back to that original ratio, again, having now removed the RT, of doing the integral of 0 to f versus 0 to p for this 1 over p dp. Now, what we can do is, hey, we already have an expression for non-ideality. We can go ahead and replace that 0 to f by doing 0 to p, but now instead of the ideal expression of 1 over p, we can do the real expression of z over p. So we've now introduced our fugacity coefficient in terms of our compressibility, which we've already talked about in chapter 1. We have some ways to determine the compressibility of a non-ideal gas, especially if we use the virial expression. Now, in this case, note the z is a constant, so it's going to be a lot easier to go ahead and combine these two terms. And so what we have is the integration from 0 to the final pressure of z over p minus 1 over p dp. And sorry, z is not actually going to be a constant. Z is going to have some pressure dependency, but we have some expressions for this. So it turns out if we actually want to get our fugacity coefficients, one of the best ways is going to be determining the natural log of the fugacities by integrating this z minus 1 over the pressure as a function of the pressure. So this does mean that in order to accurately determine the fugacity coefficient, either I need very good experimental data, which will give me the z at all of these pressures, and I can integrate it numerically, or we're going to have to determine the z in terms of other features. The easiest one here is, again, using the virial coefficient, but indeed you can also do this for things such as the van der Waals equation. But what this does is it allows us to determine the fugacity coefficient in terms of an equation of state for the relevant gas. And again, notice we are going to have this pressure dependency. So let's look at what this looks like in terms of reduced variables. So it turns out if we have the reduced variables, we can determine the fugacity coefficient in terms of the reduced pressure and the reduced temperature. So notice that if we have, as we increase the reduced pressure, not too surprisingly, when we're at a significant fraction of the critical pressure, the system is behaving very non-ideally. And then again, at very high temperatures, it will behave more ideally, which makes sense. And at low temperatures, it behaves less ideally. Now, this less ideal behavior at low temperatures occurs not only when we're looking at high reduced pressures, but also at low reduced pressures. So again, just as a good callback to chapter 1, remember at very low temperatures, the system will become more attractive, but we're now also seeing it will become more repulsive at high pressures with, again, this high pressure dependency because it feels those other interactions more acutely and will have more inelastic collisions. So again, this also shows that if you know your reduced variables, you can find tables like these in a lot of chemical engineering literature to determine the fugacities, which will let us figure out how additionally stabilized or destabilized the system is. Now, one of the reasons why these are often very important is they can change a lot of phase behavior. So remember, all of our equations for pressure dependencies of gases are going to assume ideal gas law. But if you want to go ahead and treat them for a non-ideal scenario, you can simply always substitute in pressure for fugacity and the same equations will work. But again, we're just substituting it in for these Gibbs expressions. So next time, we're really going to dive in to how we can try and apply these systems by starting with a big overview look at phase behavior. Next time, we're starting chapter 4 and looking at phase transformations. Until then, take care.